A warm welcome to the 7th session of the chapter Haloalkane and Haloarenes. Of course, the last unit, the last session of this chapter called stereochemical aspects on SN1 and SN2 mechanism. Of course, the 5th session which I discussed was SN1 and SN2. So we are in the 7th session of the chapter Haloalkane and Haloarenes. Okay, now coming to the stereochemical aspects on SN1 and SN2 mechanism, what we are going to discuss here, or what we are trying to learn here, is what happens to the organic compound when a plain polarized light is passed. So I will recollect the memory from the first year. That is, you discussed about something called as isomerism, right? You have discussed about isomerism, you have discussed the two types of isomerism, that is structural isomerism and stereoisomerism. In coming to structural isomerism, last year we have discussed chain isomerism, position isomerism, functional isomerism, metamerism and tautomerism. That comes under structural isomerism. But the second part, other division of isomerism, is geometrical isomerism and optical isomerism. Of course, geometrical isomerism you have discussed last year, that is cis and trans. Okay, so that you have discussed. Second part, that is optical isomerism, which we are going to discuss here and apply the concept on SN1 and SN2 mechanism. What happens to the stereochemical aspects of SN1 and SN2? So hopefully you have understood SN1 and SN2 mechanism, which we have discussed in the 5th session. And now to go to that idea, what happens to the aspects on SN1 and SN2, I need to start from the basics to tell you what is this optical isomerism. Now coming to the optical isomerism, see, when compounds having same molecular formula but differing in the direction of rotation of the plane polarized light, they differ. The two organic compounds, one will both will show optical activity, but one may rotate in the clockwise, the other may rotate in the anti-clockwise. So the compounds having same molecular formula but differing in the direction of rotation of a plane polarized light. So I must discuss what is plane polarized. I will explain to you all. Are called optical isomerism. This phenomenon is called optical isomerism. So if I take an organic compound, a solution, and pass this PPL, the display of polarized light, the light which comes out, whether it goes to the right or to the left. They rotate either to the right side or to the left side. Now that decides, that is what we are going to discuss, called as optical isomerism. Now second question you will ask me, do all the organic compounds are optically active? No. There is a criteria, there is a condition, and I of course at the end of the session will be able to identify which is optically active, which is optically inactive. How can we decide an organic compound is optically active? What are the qualities of an organic compound to show optical activity? That will come to the end of the session. You will be able to analyze any given organic compound. You can check whether it is optically active by two conditions which I will discuss in the session here. What is optical activity? The property of the substance, the property, want to call a compound, organic compound A or B, that organic compound optically active. Why we call them optically active? Why? Because they show optical activity. What is optical activity? The property of the substance rotate, again the same idea, the property of the substance rotate the plane of polarized light is called optical activity. Again, the ability of the organic compound to rotate the plane of polarized light is called optical activity. And all the substance, I told you, all the organic compound need not be optically active. There are few which are optically active and few which are optically inactive. So we have to characterize them and then take for our study, that is, we call them optically active substance. Again I am going to define the same thing. The compound which can rotate the plane polarized light are called optically active substances. So which have ability to rotate the plane of polarized light, such compounds are optically active substances or optically active compounds. So I told, I am making very clear, all the organic compounds need not be optically active. And now we are trying to remove that optical inactive outside, and we will try to get all the optical active compound inside and try to learn why they are optically active. Then and then again I am trying to tell you plane of polarized light or plane polarized light. So, is there any difference between ordinary light and a plane polarized light, and how to get the plane polarized light? We will try to discuss about that. So, what is a plane polarized light? Only if I pass the plane polarized light, there we can expect the rotation of the light either to clockwise or to the anti-clockwise. I can't pass the ordinary light. So, I need to prepare I need to get a plane polarized light. How to get a plane polarized light? So, what is the idea of ordinary light? See, ordinary light we say where the waves oscillate in all direction. In all direction they oscillate. If I pass this inorganic compound, the organic compound, even though it may be optically active, it may not exhibit optical activity, because here you can see this is called ordinary light. You can see oscillation in all directions. The waves are oscillating in all directions. If I pass this inorganic compound, I cannot expect any optical activity. So, I must get a plane polarized light. I will show a difference between ordinary light and a plane polarized light. So, I pass this light through a nickel prism. I will pass this light through a nickel prism. Of course, we will not go in discussion what exactly happens inside. Of course, physics will teach us what is going to happen there. When the light passes one medium to another medium, there is some change. When light passes from one medium to another medium, there is a change. So, now as this ordinary light will pass through a nickel prism, right? The light which comes out will oscillate, the waves will oscillate only in one particular plane, only in one particular plane, only in one particular plane, and this is called plane polarized light, PPL. So, I will repeat again, there is a difference, you can see difference there. Ordinary light oscillation in all direction, plane of polarization oscillate only in one direction. Now, if I take this PPL and pass on a solution, an organic compound, it has two ways to go. Either the light will go in the right side or in the left side. If it is optically active, if it is optically inactive, then the light will not have any source of deviation, it remains the same. So, now this is what we are trying to help, because without, see, always I am speaking the same thing, plane polarized light, here also plane polarized light. So, I am given information to you when the difference between ordinary light and a plane polarized light. When I take the ordinary light, pass through nickel prism, and when the light comes out, it comes out with a plane polarized light. The difference is it oscillates only in one direction. That light has to be used to check whether the compound is optically active or optically inactive. I will cross check once again. Optical isomerism I told you, then optical activity I have explained to you. All the organic compound are not optically active. The compound which rotate the plane polarized light are optically active substances. Then we discuss about plane polarized light. So, as we just discussed about the plane polarized light, now I will have to separate what are the compound which optically active rotates right hand, that is clockwise. What do you call the organic, how do you specify or separate, symbolize the organic compound rotates in the anti-clockwise, and what happens if the organic compound rotates equally clockwise and anti-clockwise, whether it is optically active or optically inactive. So, we are trying to proceed further. So, I am passing the PPL, that is plane of polarized light, an organic compound. If the compound rotates, so we are discussing about optically active compounds. So, this compound will rotate. Now, remember, if the compound rotates the plane polarized light to the right, that is clockwise. So, I told you, if I take a solution, pass the PPL, the light which comes out, of course, we need to check with a polarimeter we call it as, just check whether how far it deviates. Okay, we call the instrument used to check the deviation. Okay, if the compound rotates the plane polarized light to the right, that is clockwise. What is the name given for them? How do you separate again? Optically active, again you are separating two, clockwise, anti-clockwise. Now, how do you separate them? What do you call them as? It is called dextro-rotatory or D form. We write D before the name of the organic compound. So, whenever I write D, it is called dextro-rotatory. Dextro means clockwise or D form, or we also can say it is indicated by a plus in the bracket, plus sign before the name of the organic compound before. So, example is plus, the moment plus comes wherever in the organic compound before the name of the organic, before the name, it indicates point number 1, it is optically active. Point number 2, it rotates the plane of polarized light to the right, or we can also call it as a D-lactic acid. D-lactic acid, of course, I will write the structure later and I give an example of enantiomers. So, how to name, I am just trying to explain. Plus lactic acid, D-lactic acid, the moment plus comes, it is optically active, rotates to the clockwise, dextro-rotatory substances which are optically active. Now, what happens if the compound rotates in the anti-clockwise? Okay, the compound rotates the plane polarized light to the left, that is anti-clockwise direction, that is anti-clockwise direction, that is it goes the left side. Now, what is how do you separate them? What do you call them, sir? It is called levo-rotatory, L-A-E-V-O, levo-rotatory compound, or we call L compound, or we call it as a minus in the bracket and we write the name of the compound. Now, example L-lactic acid or minus lactic acid. So, dextro is also optically active, levo is also optically active because they have the ability to rotate either to the clockwise or to the anti-clockwise. The last one what we discuss, if in case we find an organic compound which rotates equimolar. What is equimolar? Equally, both clockwise as well as anti-clockwise. If an equimolar rotation of clockwise and anti-clockwise leads to form a racemic mixture, racimization, racemic mixture. Now, what happens here? We call the plus or minus in the bracket or DL form. Is it optically active? No. Racemic mixture is optically inactive. Why optically inactive? Why optically inactive? It is optically inactive because it rotates clockwise 50%, anti-clockwise 50%. The molecule remains at a state where it does not show any rotation because equal rotation to clockwise, equal rotation to anti-clockwise, of course both cancel, and the organic compound is optically inactive because it shows equimolar rotation. Okay. So, this is how we are trying to characterize the organic compound which rotates clockwise, dextro-rotatory, anti-clockwise, levo-rotatory. If it rotates equally on both the sides, it is called as racemic mixture. So, after getting this information, the next question you will ask me, sir, how can I identify by seeing an organic compound it is optically active or inactive? That is our next journey where we will try to find out and learn things to identify whether the organic compound is optically active or optically inactive. That is our next part, which I will continue with knowing this dextro, levo, racemic mixture, and next we will learn how to identify. So, we are now trying to learn to check whether the organic compound is optically active or inactive. Okay. So, if it is optically active, how to check? What are the criteria for an organic compound to be optically active? That is either dextro or levo. How to identify whether the compound is optically active? First thing you must find out and learn first molecular symmetry. Now, molecular symmetry is an imaginary line or imaginary plane which divides the organic compound, which divides the molecule into identical halves, and we say by a plane or by an imaginary plane, by a plane known as plane of symmetry. The molecule is symmetrical molecule. The molecule is symmetrical molecule. We say that the molecule that does not have plane of symmetry is called asymmetric. So, get an idea of. If a molecule has a plane of symmetry, the molecule is symmetrical molecule. If the molecule does not have plane of symmetry, is a asymmetric molecule. Point number 3, very important for us. molecule is optically active if it does not possess plane of symmetry. It should not have plane of symmetry. Now, I will give an idea, brief idea, what is a plane of symmetry. If I take a circle or if I take a ball here, like, okay, if I take a ball, now I will divide the center, I just draw a line. If I draw a line exactly at the center here, the ball gets into two halves. If I open it, both are identical. Similarly, we can also have in the organic compound called plane of symmetry. The idea is what? If I divide a molecule and if I draw a line at the center, if the molecule is divided two identical halves, if two identical halves are there, one is a mirror image of the other, two identical halves, then we say it is called as a molecular symmetry. Check whether the organic compound has plane of symmetry. If it does not have plane of symmetry, it will show optical activity. First qualification, first criteria, first condition is a molecule is optically active if it does not possess a plane of symmetry. What is plane of symmetry or a molecular symmetry? An imaginary line which divides the molecule in two identical halves is called molecular symmetry. Let me give an example to you. Okay, if I give an example, I'll come to the last, to lactic acid. I can give an example there. Second condition, molecule should be chiral. What is the chiral molecule? How to check chiral molecule? What is the chiral molecule? A molecule which is non-superimposable on its mirror image. What is non-superimposable on its mirror image? A molecule which is non-superimposable on its mirror image is called a chiral molecule. Point number one. Point number two, such molecule does not possess a plane of symmetry. I told you here, point number three, a molecule is optically active if it does not possess a plane of symmetry. And a chiral molecule does not have a plane of symmetry. Two conditions are coming now. One, check whether plane of molecular symmetry is there. No plane of symmetry, and if the molecule is chiral, then we say it is optically active. What is a chiral molecule? How to check chiral molecule? I will come to chirality center. What is chirality center? A carbon bonded to four different atoms or groups. I will repeat here. A carbon bonded to four different atoms or groups in the molecule is called chiral carbon, or we call chirality center. A chiral carbon, or we call chirality center. Check whether carbon has four different groups, and check whether the carbon, whether this molecule has a plane of symmetry. Let me take an example of lactic acid. So lactic acid is COH, CH3, HCOH. All four different groups are there, and this molecule is chiral. Point number one. Point number two, you cannot have a plane of symmetry. You draw anywhere, you will not get two identical halves. So if you don't get two identical halves, then this molecule is going to be asymmetric. Here, asymmetric molecule does not have plane of symmetry. Asymmetric molecule. First condition satisfied. Does not have plane of symmetry. Point number two, check whether the molecule is chiral. Yes, the molecule is chiral. It does not superimpose on its mirror image. Why? Because the mirror image of this will be, OH will be on the left hand side, H will be on the right hand side. You cannot superimpose the mirror image of lactic acid. So point number two, satisfied. Its chiral carbon is there. Yes. Does it have a chirality center? Yes. Therefore, this molecule is optically active. See, two conditions very clear. So I bring some molecule which is, you can find a plane of symmetry. So I will bring a molecule here. COOH, COH, H, COH, H and COOH. Now see this molecule here, just for information, it is called tartaric acid. We will come to this concept here. Definitely a student will try to explain, it has a chiral carbon. Yes, it has more than one chiral carbon. Yes, definitely. But does it have a plane of symmetry? Yes. If I draw a line, imaginary plane between second carbon and the third carbon, we can find two identical halves. That means it is optically inactive, even though this compound called tartaric acid has chiral carbon, but it does not, it has a molecular symmetry. Even though it is chiral but has a molecular symmetry or a plane of symmetry, it is going to be optically inactive. So you should have two qualities to check whether the organic compound is optically active or inactive. Check whether the molecule has a plane of symmetry. If it does not have plane of symmetry, check second point whether the molecule is chiral. If this two does not have plane of symmetry but has a chiral carbon, is a chiral molecule, then this organic compound we can call it as an optically active. So you can see this is plus lactic acid, dextro rotated lactic acid, and the carbon is chiral. The carbon is bonded to 4 different groups. It has one chirality center. It has no plane of symmetry. Therefore, this is optically active. So this two condition, if you learn with getting more molecules, of course in your textbook you have one exercise is there. You can just check it out. In that they are given how to check asymmetric and symmetric carbon, asymmetric carbon and symmetric carbon. So if you check that, you will get an idea, and check again whether they have plane of symmetry. That one exercise will make you learn how to identify optically active compounds. Of course, when we learn few more examples, you will definitely get an idea whether the compound is optically active or not by having two qualities. As we come towards the third part, that is enantiomers and meso compounds, where now you will get an idea how to find out optically active. I just repeat once again, two conditions. Condition number 1 is a molecule should not possess a plane of symmetry. Point number 2, the molecule should be chiral, should not possess a plane of symmetry. Now what are enantiomers? Usually 2-mark question in the board exam. What are enantiomers? Enantiomers are optically active isomers. They are optically active isomers which are non-superimposable mirror images of each other. So it's the isomers, 2 isomers are there. And one more point, how to identify. See, you have 2 things, plus dextro rotated lactic acid and levo rotated lactic acid. Of course, structure tells us it has one chiral carbon and no plane of symmetry, optically active, one chiral carbon, no plane of symmetry, optically active. Both are optically active, but what is the idea? Which are non-superimposable mirror images of each other. I cannot superimpose the mirror images. These are called enantiomers. Now, what is the difference? How do you find differences? Both the molecular formula remain the same. Both the molecular formula remain same. So we say enantiomers have similar physical and chemical properties. They both will have similar physical and chemical properties, except for their rotation. One rotates the plane polarized light to the clockwise, another rotates the plane polarized light to the anti-clockwise. Except this, all the properties of a physical property and chemical property of plus lactic acid and minus lactic acid remains the same. Therefore, that's what we give a note here. Enantiomers have similar physical and chemical properties except for their specific rotation. So that are enantiomers. So we are going to learn still more deep about the ideas of the enantiomers and the optically active isomers. And now we are coming to the meso compound. What are meso compound? A compound having more than one chiral carbon, but optically inactive. Why optical inactive, sir? Even though it has a chiral carbon, because due to the presence of element of symmetry called plane of symmetry is called meso compound. So meso exists in 3 forms. Tartaric acid exists in as 3 forms. That is, one is plus tartaric acid. Now we check, it has more than one chiral carbon but has no plane of symmetry, therefore it is a plus tartaric acid. No plane of symmetry, has more than one chiral carbon. Now coming to the minus form, again no plane of symmetry, more than one chiral carbon, therefore it is called minus tartaric acid. More than one chiral carbon but has a plane of symmetry, therefore it is called meso compound or meso compound. The compounds are the compound which have more than one chiral carbon but optically inactive due to the presence of a plane of symmetry is called meso compound. So we are now journey is identification of optically active, optically inactive. If the optically active, we have 2 categories. One is enantiomers and one is meso compound. Plus lactic acid and minus lactic acid are a good example for enantiomers. Of course, tartaric acid has 3 forms: plus form, minus form, and one is a meso form. Plus tartaric acid, minus tartaric acid, and mesoform. Mesoform is optically inactive. So enantiomers are one of the important questions frequently asked in your board exam. So coming to the next topic called retention. Okay, what is retention? Retain, retention. See what happens here, if the relative spatial arrangement, of bonds at a chiral carbon, the carbon is chiral. What is the chiral carbon? The carbon bonded to 4 different groups, or 4 different atoms, or 4 different group of atoms. In a chiral molecule remains the same before and after. Before and after the chemical reaction, if it happens, the reaction is said to proceed with retention of configuration. The reaction is said to proceed with the retention of configuration. Let me give an idea. See how to identify whether the organic reaction which has happened is retention. You just find out here the Y minus is going to replace X. Now Y will replace X around the chiral carbon. Here carbon A, B, X, the small c is there. Okay, so I have written difference is capital C and small c. 4 different groups are there. The chiral carbon. My duty is to just remove this X. The Y can remove X just by removing X. The Y replaces X. See here, it has replaced, but all the bonds stereo center around the bond remains the same. The structure remains the same. So we write here, configuration around the stereo center remains same, around the chiral carbon remains the same. Therefore, it is called retention. You may attack a nucleophile, you may bring a nucleophile, but the nucleophile will not disturb the configuration around stereo center. It just replaces an halide, and that it forms, that is XXCABC is connected to YCABC. Y has replaced X without changing the configuration around the stereo center, around the chiral carbon, it remains same. Let me give an example to you. If I take an example, when minus, minus sign shows it is a levo, rotatory. Minus 2-methyl butane 1-ol is heated with a concentrated HCl, okay, constant HCl with its plus 1-chloro-2-methyl butane is formed without any change in the configuration. There is no change in the configuration. What has happened? Here you can see removal of water has occurred in the place of OH. The Cl has taken its place. The Cl has taken its place around the chiral carbon. The stereo center carbon, the configuration remains the same. So as we journey through the optical isomerism, the stereochemical aspects, one of the important aspects is to find out whether the retention has occurred, and if in this type of what is retention? The stereo center configuration remains same before and after the chemical reaction. Of course, we would have replaced a nucleophile, but the configuration remains same, like minus 2-methyl butane 1-ol, when attacked with HCl, react with HCl, the chlorine replaces the OH, but when I check this configuration, it remains the same. This is idea of retention. Okay, coming to the idea now, we just finished retention. Retention is the stereo center, the bond will remain the same, and the configuration also will remain the same, only replacement will take place. But now we will know 3 types: inversion, retention, and racimization. When a bond to the chiral carbon is broken, the chiral carbon means, again, I will just remind you all, the carbon atom bonded to 4 different groups is called chiral carbon, chirality center. Now when a bond to the chiral carbon is broken, there are 3 possibilities. So let me take this as a molecule. This is a compound. Now I replace Y minus, X is my target. So Y minus will replace X. Now see this same, if A is going to be the product, Y has replaced X. Now the Y has occupied the place of X. Now but A, the retention, the configuration remains the same, the configuration has not changed. The stereo center configuration remains the same. Only thing I have replaced is Y. That means what they say, if A is the only compound obtained, the process is called retention of configuration. That is about the product A. One more possibility is B. Now Y is going to replace here, the Y is going to replace X here, that is Y is going to replace X, but see the idea here. Y when replaces X, the bond around the chiral carbon stereocenter undergoes a change, and the process is called inversion. So what is happening? The Y which replaces X but replaces in the reverse order. That means this inversion is taking place. You can see the difference between the A and B. A is retention and B is inversion. So what is the concept here? If B is the only compound obtained, the process is called inversion of configuration. The process is called inversion of configuration. Point last one. You see, if both are equimolar, if I get a product A plus B together, that is a mixture. The third one, you see, if an equimolar mixture of A and B is obtained, the process is called racimization. So coming to these three ideas, we now apply these three: retention, inversion and racimization on an optically active haloalkane which undergoes SN1 and SN2 mechanism. So I remind once again, if A is the only product to be obtained, then it undergoes retention. If B is the only product to be obtained, then it undergoes inversion. If E and B are an equimolar, it undergoes racimization. So you know, racemic mixtures are optically inactive because it has both dextro and levo equally. Now coming to the application part, of course this is what our climax at the end of this chapter, which I am trying to explain to you all after learning so many things of optical isomerism. Now I will come to the idea in SN1 reaction, right? In SN1 reaction of an optically active haloalkane, a racemic mixture is obtained. Let me go to the SN1 mechanism. Is a two-step mechanism. The first is the formation of a carbocation, second one attack of nucleophile. Same thing is going to happen here. So if I take an example of 2-bromo-octane, so 2, 3, 4, 2, second carbon has 2-bromo-octane, 2-bromo-butane. If I take 2-bromo-butane, that is 1, 2, 2 plus 2, 4 here, 2-bromo-butane on hydrolysis gives plus or minus butane to all. When the word plus or minus comes, this undergoes a process called racimization, or we call racemic mixture. Now what happens in the first step? Of course, same thing what we learned, SN1 mechanism, formation of a carbocation, and next attack of OH. Now see the liberty of nucleophile OH minus. The OH minus will form dextrorotatory and the OH will attack and form a levorotatory. That means we say an optically active haloalkane which undergoes SN1 will lead to the concept called as racimization. The product will be plus or minus butane to all, plus or minus butane to all. That means what is the application part? SN1 mechanism of an optically active haloalkane undergoes a process called as racimization. What is racimization? Equimolar mixture of both dextro and levo, plus and minus. Which is optically active? No, it is optically inactive. That means we are getting a product dextro and levo equally. Now what in SN2? In coming to SN2, we are trying to learn what happens in SN2. If I take in SN2 reaction of an optically active haloalkane, a product with inversion of configuration, here the product with racemic mixture SN1, SN2, inversion of configuration is formed. For example, minus 2-bromo-octane reacts with NaOH to form plus octane to all. Now remember, the OH minus should replace Br, but of course it replaces Br. But what is happening? The bond is getting reversed. H is going to other side. The bromine where OH attacks come to the rear side, it moves other side. That means there is an inversion. Of course, CS3 and CS13 remain same. But think about bromine. OH should replace an halide. OH should replace an halide. As OH replaces an halide, it undergoes a process called as inversion of configuration. So we are very clear. SN1 and SN2 SN1 will follow racimization. That's what I told you when I was discussing about the differences between SN1 and SN2 reaction. I told one point we'll discuss after stereochemical aspects of SN1 and SN2, and then I am coming to the difference now. In SN1, racimation is obtained with optically active haloalkane. That means SN1 undergoes racimization. SN2, the product with inversion of configuration is formed with an optically active haloalkane. So we are coming to the end of the stereochemical aspects on nucleophilic. That's our idea. Stereochemical aspects on SN1 and SN2 mechanism. This is the end of this chapter, the unit 7, that is the application of stereochemical aspects on SN1 and SN2 mechanism. Now, as we are trying to come to the end of this session 7, we are just trying to know some few questions I am giving. Of course, all are important. They are just to make you recollect your memory as you go through the session to the video. So you will just get some recollection at the end of the session. What are enantiomers? I told you what are chiral carbon. Define a plane of symmetry. And then what are meso compounds? Along with that, try to get the last difference what I told you. SN1 undergoes racimization, SN2 undergoes inversion of configuration. Get that one idea. So this assignment 7, of course, I would just recollect few terms so that you will get an idea at the end of this session, that I discussed about what is an optical isomerism, optical activity, optical active compounds. Then I discussed Dextro, levo, Racemic mixture. Applying this on enantiomers, meso compound. Then I explained retention. Retention, one example I explained to you. Then I turned towards retention, inversion and racimization. Applied that on SN1 and SN2. This is just an outline of what I taught you in the session 7. Hope this chapter, as we are coming to an end, we have come to an end of this chapter. Hope you are going through the sessions regularly, writing down a note there, and hope your journey of this chapter has come to an end. And please try to write down notes of all the sessions which I have completed. And if you have any doubts, please download or send to the link which I have given in below the YouTube. That link is given. Please send it to that. So hope this one chapter as I have completed. It is a good journey with you all virtually. God bless you. Thank you so much. God bless you. Thank you.